Okay, so welcome back. Yesterday I tidied up kind of the last bit of Chapter 1, gave a brief review of the highlights of Chapter 1. So now it is time to move on to Chapter 2, which is like the middle third of the course. Probably more like, honestly, in terms of time spent, even though it's middle third in terms of chapters, right? There's 3 total chapters. We actually probably spent about 50% of the class time on Chapter 2 stuff, so it's more like half the course. It's definitely the part of the course that's stressed. This is the real meat of any differential equations course. A first course in ODEs is definitely the most important bit. So what is the topic of studies? Higher order linear differential equations. So with the exception of one topic that will come very late in the course at the very end of Chapter 3, from now on everything is going to be linear. So higher order linear differential equations. Okay, so everything is going to be linear. The reason for this is, remember, the second you had a nonlinear equation, you didn't have a nice, like kind of concise way of saying like, oh, this is the form it has to take, right? If you said something like that, then you had to be way too general. You had to say, okay, it's dy dt is equal to big F of ty, but that big F could be whatever, right? For a nonlinear equation. So that doesn't tell you that much. So the idea is that we want to, there's a number of reasons for this. One, nonlinear equations are just way harder in general than linear equations. So So we want to do away with that. Also, this is just a nice organizational thing. We can actually write out what a linear, higher order linear differential equation has to look like. Okay, so then what does a general higher order linear differential equation look like? Let's say that I have already divided through, right? I've put it into linear normal form. So we know for a first order equation, linear normal form looked like this. This was y prime plus a of t y is equal to f of t, right? This was linear normal form for us. So of course we know that in the given problem statement, right, I could have like another function of t multiplying y prime here, but all the things that we did in order to solve this equation, we did assuming we'd put this into linear normal form. So we divided through by any coefficient functions to get this thing, okay? So for a higher order, so for an nth order differential equation, maybe if I write, let's write what a second order linear differential equation would look like, and say that I've already divided through here. So let's say this would be y double prime plus, I'm just going to write it like this for now. I'll say like a of t y prime plus b of t y is equal to f of t. Okay. So this would be the linear normal form for a second order equation. And I want to continue that on. Now, of course, I'm going to run out of letters in the alphabet if I'm doing this for completely general n. So what would this look like for an nth order thing? Like what kind of notation could I use? So for nth order, what am I going to have? Well, I'm going to have my highest derivative term showing up, which is the nth derivative of y, plus, I'll say this is a sub n minus 1 of t times the n minus first derivative of y, plus, and so on, all the way down to a sub, we'll say this is like a sub 2 of t times y double prime, plus a sub 1 of t times y prime, plus a naught t times y is equal to f of t. So this is what my completely general nth order linear equation looks like. So an nth order linear equation looks like this. Okay. Now, some terminology to get you going here, right? So these functions are called the coefficient functions. These are the coefficient functions for this differential equation. Okay. So these are called the coefficient functions. Now, in the first order case, we didn't really, the only coefficient function here was just this a of t. We didn't really put any restrictions on what that a of t could be, right? We were happy if it was whatever. So it might surprise you to know that for a huge chunk of, for almost the entire chunk of our higher order stuff, we're actually usually going to assume that these coefficient functions are all constant. Okay, that might seem like a really strong assumption to make, but the reason for this is it's way too complicated if you allow these to not be constant. It's called variable coefficients. We are going to see how to solve variable coefficient things, but there's a catch to it. Okay, so it is a complicated thing for higher order equations. Even for second order equations, this is vastly more complicated. It's not quite as simple as it is in the first order case, to say the least. So for the most part, we are going to consider constant coefficients. So an equation with constant coefficients means all of these a sub I of t are actually equal to just real numbers. So all of these are constants. Okay. So all of these are just real numbers. And that's it. So they actually don't depend on t. If not, we call them variable coefficients. And as I said, we are going to see examples of variable coefficient problems. We are going to have a single way of dealing with that. But in general, when we're dealing with higher order linear equations, we're going to be in the case of constant coefficients. You'll see why this is eventually. Okay, so there's that. Now, some more terminology here. So in addition to us typically considering constant coefficients here rather than variable coefficients, the right-hand side function, right? So, of course, when this was 0, right, that was a special case. I might have even named it back then. I can't remember. But when the right-hand side function is 0, that's what's known as a homogeneous equation. So a homogeneous nth order linear equation would look like this, except the right-hand side would be 0. If this f of t is not 0, if it's just some function of t, that's what's called an inhomogeneous or non-homogeneous problem. So let me rewrite this again. So then maybe I'll write it out like this. Constant coefficient nth order linear homogeneous equation. So constant coefficient, nth order linear, homogeneous equation. What does that look like? That is like nth derivative of y plus a sub n minus 1, which is just a constant, times y, or the n minus first derivative of y, and so on, all the way down to a sub 2 times the second derivative of y plus a sub 1 times y prime plus a naught times y is equal to 0. Okay, so that is constant coefficient, nth order, because the nth derivative is the highest one showing up. Homogeneous, the right-hand side function is 0. So constant coefficient, nth order linear, non-homogeneous or inhomogeneous, sometimes you'll hear this called. Well, it looks exactly the same on the right or on the left-hand side, so this is what it looks like. And now, why is it important to be able to distinguish between all these? So these look all the same, so now the right-hand side is an f of t, not just identically 0. So this is the difference between homogeneous and non-homogeneous. Okay. So why is it important to be able to distinguish between these things immediately? So you are not going to immediately be shown how to do this in complete generality, because that wouldn't make any sense. So we have to build up this process from simpler and simpler cases. This is the case that's going to kind of illuminate to us exactly what's going on. So this is actually the case that we're going to be doing first. Okay, so the first thing we're going to be doing is constant coefficient, nth order linear, homogeneous equations. This is what we're going to be doing. Okay, this is our first object of study. Now the reason that we're picking this is, well, it's the simplest possible case, right? We made everything as simple as possible. So it's nth order linear, so it's already this nice form, and everything is going to be linear, like I said, from here on, just because this is going to make our lives easier, so it's something we can actually do. All of these coefficient functions are constants, right? Again, that's typically what we're going to be assuming as well. And the right-hand side is 0, so this is a homogeneous equation. So this is as simple as we can get it. All right, and we're going to see how being able to solve this tells me something about how I can construct solutions to this. So that's our goal. And once we know how to do that, we will be mostly done with Chapter 2. We'll only have a couple more things to say, really, about Chapter 2. So this is going to be something we spend a decent chunk of time on. Okay, so this is the case that we focus on for the most part. Okay, so here's a few facts. So for now, assume we have an nth order linear constant coefficient homogeneous equation. So nth order linear constant coefficient homogeneous equation. That's this one. Okay. All right, so this is going to be our object of study. Now, what's kind of the first thing to note? Recall, in the first order case, so in the first order case, we had y prime plus, I'm going to write it as a naught y, following this, and that is equal to 0. In this case, there was a really kind of easy answer as to what the solution was. So in the homogeneous case, right, you can rewrite this. So this is the thing we have. In the first order homogeneous case, this means y prime is equal to minus a naught y. But we know what a solution to this is, either from the recipe or from this relationship. This was just c e to the minus a naught t, right? And so this was our general solution. Any solution had to be of this form. This was an infinite family of solutions parameterized by this constant c. Okay. All right. Let's go to the second order case. This is the second order case. So let's say we have y double prime plus a1 y prime plus a naught y is equal to 0. Now we will see, soon in the coming lectures how we're going to go about solving this thing generally, but I'm not going to do that now. Okay, so I'm not going to do that now. The question, right? How many solutions does this have? You might think that's a pretty silly question because in the first order case, the answer, of course, like the easy answer to say is it has infinitely many, right? Every choice of C gives you a different one. So it has infinitely many parameterized by a single real parameter C. So it's probably not, a bad guess here to say how many solutions does this have? It has infinitely many. But that's not really the question I'm asking. What I'm really asking, right, I just don't want to have to try to word it in an awkward way. What I'm really asking is this, are the solutions parameterized in a similar way? Is it an infinite family of solutions parameterized by a constant? Or is it maybe a couple of infinite families of solutions parameterized by different constants? So then here is a nice fact, and one of the reasons why we impose linearity here. You might remember a similarly named fact from linear algebra. So this is the superposition principle. If y1 and y2 are both solutions to a linear nth order differential equation, as in this case. Okay. Then so is y1 plus y2, and more generally, so is any linear combination of y1 and y2, i.e. some cy1 plus dy2, where c and d are constants. So c and d are some real numbers, cy1 plus dy2, where c and d can be whatever real numbers you want. That is also a solution to the same differential equation. Okay. So this is very different from the nonlinear case, so you don't get this at all if you have a nonlinear differential equation, but this is what you get immediately. You can verify that real quickly here, right? So if y1 and y2 each separately satisfy this, to show that y1 plus y2 also does, let's just plug it in here. So I get y1 plus y2 double prime plus a1 y1 plus y2 plus a naught times y1 plus y2 is equal to, well, what is that equal to actually? Yeah, I'm not going to write 0 because then I'd be done. So what is this equal to? Well, oh, sorry, there's a prime here. So this thing, the derivative itself, right, is linear. So this becomes y1 double prime plus y2 double prime plus a1 y1 prime plus a1 y2 prime plus a naught y1 plus a naught y2. If you take the y1 terms, that's 0 because y1 satisfies this equation. The other terms, you take that sum, that's also 0 because y2 satisfies that equation. So this is equal to 0. So y1 plus y2 also satisfies the same differential equation. Like I said, this is something that does not work if the differential equation itself is nonlinear. Okay, so this is very important. Having linearity is very important for this. So this tells you sort of a way that you can construct different solutions, right? Given two solutions, y1 and y2, adding them is some other solution, right? Now, that's not that surprising if you go back to the first order case. So if you go back to the first order case, for instance, if a naught is equal to like 2, right? So if I have y prime plus 2y is equal to 0, then my general solution is c e to the minus 2t. Okay, so then you could say, all right, let y1 of t be like 2e to the minus 2t, right? And let y2 of t be like 3e to the minus 2t. Then y1 plus y2 is just 5e to the minus 2t. Of course, that's another solution, right? Since any solution looks like this, c e to the minus 2t. So, of course, it's another solution. But really, it's the same kind of solution, right? Okay. So let's let's do an example. Okay. Let's do an example. Let me cook up something really quickly. So I'm not really following the notes here because I think it's good to kind of have a kind of like a more broad overall introduction to this before we get to the more grindy computational stuff. So let's do a quick example then. Let's say that I have, let's do the following. Let's do y double prime plus 2y prime plus y is equal to 0. Okay. 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 So I'm going to give you some quick maybe I'm just going to say let y1 of t be e to the minus t, and let y2 of t be 3 e to the minus t. Okay. You can check that both of these satisfy this differential equation. So y1 prime is equal to, so if I take the single derivative of this is minus e to the minus t. Y1 double prime is e to the minus t. So y1 prime plus 2, or sorry, y1 double prime plus 2 y1 prime plus y1 is equal to e to the minus t minus 2 e to the minus t plus e to the minus t. So that's 0. Okay. So this one solves that differential equation. What about this one? So y2 prime is minus 3 e to the minus t. y2 double prime is 3 e to the minus t. So y2 double prime plus 2 y2 prime plus y2 is equal to 3e to the minus t minus 6 e to the minus t plus 3 e to the minus t. So again, 0. So that one also works. Okay. I'm going to give you another one here. T e to the minus t. Does this work? Well, let's check it. So what's y sub 3 prime? So y sub 3 prime is, I have to use the product rule here. So this is e to the minus t plus t times e to the minus t prime, right? So this is e to the minus t minus t e to the minus t. That's what y3 prime is. So what is y sub 3 double prime? That is minus e to the minus t minus this thing, if I take the derivative of t e to the minus t, so that is e to the minus t, all right, plus t e to the minus t times minus 1. All right, so what is this? This is minus e to the minus t minus e to the minus t, so minus 2 e to the minus t minus minus 1, so this is plus t e to the minus t. Okay. Okay. So then what do I get here? Well, y2, sorry, y sub 3 double prime is equal, or sorry, y sub 3 double prime plus 2y sub 3 prime plus y sub 3. That's equal to minus 2e to the minus t plus t e to the minus t. All right, that's what I get from this term. Plus 2 times y sub 3 prime, which is e to the minus t minus t e to the minus t. Right? Plus y sub 3, which is t e to the minus t. So if I look at this, this is equal to, so this is minus 2 e to the minus t plus 2 e to the minus t, so those cancel. And then I have 2 minus t e to the minus t plus t e to the minus t plus t e to the minus t. Those three cancel, and I get 0. So this one also satisfies that equation. Now, the principle of superposition tells me what? It tells me that the sum of any two of these is also a solution. Okay, so y1 plus y2 is a solution. But it also tells me that y1 plus y3 is another solution. Now, between the two of these, right, this y1 plus y3 gives me a more general looking solution. What do I mean by that? If I add y1 and y2 together, what do I get? I just get another thing that looks like both of them, right? I get another thing that looks like both of them. So, what do I mean by that? What I mean by that is, what I get is, like if I add y1 and y2, I get e to the minus t plus 3e to the minus t, which is 4e to the minus t. It's just another c e to the minus t, right? So I started out with two solutions that are both some constant e to the minus t. I add them together, I get some other constant times e to the minus t. These are the same kind. Now, not everyone that takes 246 has already had 240. If you have, then there's a ton of things that you probably have already thought about that's actually going on here. The idea is that we are trying to find a general solution to these differential equations. Okay, a way of saying that is we're trying to find a basis for the solution space, okay, of these things, where the basis vectors are these functions, okay, and so we want to be able to view each of these. So to say that I have a general solution to a differential equation is to say that I have a basis of functions such that a general solution, that is any solution to this, is a linear combination of those basis functions. Okay, so that's what's really going on here. That's also why we require linearity here, because this is only true for linear equations. But what am I going on about? The point is that these two types of solutions are really the same kind of solution. Yeah, they're technically different, but they're the same type. They're both constant e to the minus t. Solutions that look like this alone are not enough to fill out the whole solution space. So not enough to fill out solution space. Okay. Because we just checked that something that looks like this is also a solution. So, if I want to describe the general solution to such a problem, I would say that y of t equals c1, I'm going to say c1 e to the minus t plus c2 t e to the minus t is my general solution. Now, why do I write this? Well, this is going to cover solutions that look like this. Notice, y1 and y2, right, are both examples of this where I've taken c2 to be 0 and c1 to be 1 in the case of y1, or 3 in the case of y2. But notice that I have to include a term like this, because if I don't, right, if this term doesn't exist, then this cannot possibly be the general solution to this equation. Why? Because, well, this y sub 3 I verified is a solution to the equation, but it's not of this form. Right? T e to the minus t is not the same as constant times e to the minus t. But if I include this second term, then it is the same as choosing this constant to be 0 and my second constant to be 1. Okay? And so, I'm not going to prove yet, but we're going to see that this is the expected result. That I have a second order differential equation here, right, that's linear, constant coefficients. And just like in the case of a first order equation, the solution space is parameterized by some constants. So there's an infinite family of solutions here. So there's infinitely many solutions to answer our question of how many solutions we had. Infinitely many solutions. But now that I'm in the second order case, this infinite family is actually parameterized. It's actually really two infinite families, right? E to the minus t and t e to the minus t. So each of these are parameterized by a constant, a different constant. So C1 and C2. Do we know from this that there isn't a third term? So Nick, the thing is that from what I've said, I would need to say more to explain why there's not a third term. But it turns out that there can't be more than two here. There can't be more than two. There needs to be exactly two to make this work out, and that has to do with the order. There is an argument that we'll make. This requires some linear algebra understanding. But basically, the argument is that the order leads to the number of arbitrary constants you need in order to fill out the solution space. Okay. Now, we're about to describe what it means to fill out the space and how we determine that. But I wanted to give you the general picture. So more generally, an nth order equation, so an nth order linear equation, maybe I'll write it like this. And nth order linear equation that's homogeneous with constant coefficients. So this is what we look like. This has general solution y of t, which is c1 y1 plus c2 y2, so on, plus cn yn, where the ci's are constants and y1 to yn all solve the differential equation. Here. And so this is the superposition principle for linear differential equations. Okay, so it's that I can build up the general solution as a generic linear combination of some solutions to this differential equation. Now, this brings up an excellent question, right? Which y sub i's do we use to build our general solution? Why am I asking this question? So if I look here, right, notice that y1, y2, if I considered this sum, that wasn't enough to fill out the solution space. So just having y1 and y2, trying to form C, here, I'll just write it here, C1 y1 plus C2 y2, why was this no good to fill it out? Well, C1 y1 is C1 e to the minus t plus C2 y2, so that's C2 times 3 e to the minus t. So really, if I rewrite this, this is just C1 plus 3C2 e to the minus t. But 3(1) plus C32 for any choice of C1 and C2, that's just some arbitrary constant. So really, this is like big C1 e to the minus t. So even though I took two different solutions, when I added them together in this linear combination, they really only gave me one dimension worth of solutions. Okay, again, this is where, 240 makes all this stuff I'm saying way, way more intuitive and easier to easier to see what's going on. Okay, you can think of it like, well, these two things are scalar multiples of each other, right? And if you thought about them abstractly as vectors, right? If I have two vectors, right? Well, if this is what my two vectors look like, then if I consider the span of these two vectors, which is the set of all linear combinations of these two vectors, what set do I get? I get a whole plane. Okay, I get a whole plane's worth of points, okay, as the span of those two vectors. That's what I get. But if I start with two vectors, so this picture is not true for any two vectors. If I start with two vectors that are parallel, or that are scalar multiples of each other, then those are the two vectors that I get. And if I consider the span of these two vectors, that is the set of all linear combinations of those vectors, the geometric object I get is just a line, right? So if I start with two vectors, right, and I consider all possible linear combinations of those two vectors, there's a difference here between how much data or how much info I get. In this case, I get 2 dimensions worth of data, so this is a 2D picture, right? And in this case, I get 1 dimension's worth of data. This is a 1D thing. This is a line, okay? So in some case, or in some way, this is considered a degenerate case where I'm not getting as much info as I should in some sense, right? So what is the key thing that is required to get 2D, the full amount in this case? I just need these vectors to not be scalar multiples of each other. Okay. Now, translating that into the world of differential equations, and also talking about it more generally, what is required is to know that the vectors in question are linearly independent. So these two vectors would be called linearly dependent. These would be called linearly independent. So the way to think about this is these solutions here, these two are linearly dependent. What we want are to have linearly independent solutions. So which y1 do we use to build our general solution? We need a set of solutions. So these are all solutions, right? Every single one of these. So we need a set of solutions, y1 to yn, that are linearly independent. Now, again, abusing some 240 lingo, how did you know whether or not some given vectors were linearly independent in 240? Well, assuming that the number of entries and vectors was right, and it will be in this case, so we're going to be happy with that. You would, form matrix of the proper size and then take the determinant, right? And if that determinant was anything other than 0, you were happy. Okay. Now for us, the vectors that make this up are actually functions. And so the thing that functions as our determinant here is going to be slightly different, although it is itself a determinant. Okay. So it is itself a determinant. All right. So then how does this go? Well, there is a more general picture that I will address later for nth order equations, but for now I'm going to focus on the second order case. The reason for that is that although we're doing higher order equations, and we're going to cover chapter 2 material in such a way that I will show you instantly and constantly how all this stuff applies to the general nth order case, but computationally, everything we're going to be doing is for second order equations. Okay, so everything we're going to be doing is for second order equations, and this is just because to do this for higher order equations, it's just more tedious to have to do this by hand when the order is greater than 2. And you will see very soon exactly why. So we seek a set of n linearly independent solutions, y1, y2, all the way to yn, for the equation it looks like this. This homogeneous, constant coefficient, linear differential equation. Okay, so I'll define what linear independence is. Okay, if we have this, so if we have such a set, so let's say, a little bird told us the set of solutions, and we either verified that they're solutions themselves and that they're linearly independent. We know how to verify that something's a solution to a differential equation, so that's easy to check. Verifying they're linearly independent, that's something we don't know yet, but we're about to find out very soon. So let's say we've done that. So if we have such a set, then the general solution to star, that's this thing, is y of t, which is c1 y1 of t plus c2 y2 of t, and so on, all the way out to cn yn of t. So if a first order equation is parameterized by a single arbitrary constant for its general solution, and if the general solution to a second order equation is parameterized by 2 arbitrary constants, well, then the general solution to an nth order constant coefficient linear differential equation and homogeneous is it's parameterized, so this general solution is parameterized by n arbitrary constants. Okay, so there's a couple of components here, right? So this fact, maybe I'll call this fact, means that we can write out the general solution if we know how to do 2 things. So we need to know 2 things. All right, 1, what is linear independence? Independence. There we go. Okay, so what is linear independence? 2. How do I come up with this set? How do I construct this set of solutions? Going back to the one example we did, right, here was our differential equation. Maybe you look at this and say, yeah, I could have come up with that. Right, but could you have come up with this as a solution, right? Maybe this is a little bit more mysterious as to why this would work. You see how this could frequently, or how this could rapidly spiral out of control in terms of trying to guess how this goes. So obviously we need a more systematic approach here. Okay, well, this is what I'm going to do first. And this is what I'll do second. This is the more important bit, because we're going to do this in such a way. So it turns out that we will answer 2 in such a way that the solution set we build is always linearly independent. So we're actually not going to have to check this typically. Okay. So once we figure out how to actually write out solutions to this, we're not going to have to check linear independence. It's going to be automatic. But before we know how to do that, it's important to know what linear independence means here. Okay. All right. So we will do 2, and once we do 2, we will have addressed 1 automatically, as I said. But before then, what do? So first of all, such a set, so if we have such a set, so a set of n linearly independent solutions is called a fundamental solution set. Or a fundamental set of solutions. So in the notes, if you see reference to a fundamental set of solutions, this is what is meant by that. Okay. So they are solutions that are linearly independent. Now, let's finally get at what does it mean if functions are linearly independent. So first, definition. I am going to define this in general for an nth order equation, and then I'm going to specialize immediately to the case when n is equal to 2. Okay, because it turns out that if you understand the n equals 2 case, then we understand all of the higher n cases. Might not seem intuitive as to why that'd be the case originally, but yeah, it turns out that just piling on higher and higher order equations doesn't really change what's fundamentally going on. So once you can do n equals 2, you can understand how this goes for higher order things. Okay. So quick definition. If y1 to yn is if y1 to yn is a set of solutions, so let y1 to yn be a set of solutions to that differential equation that I wrote on the previous page, star, bring it back for a second. So to this thing. Okay. All right, then the Wronskian of y1, or of the set y1 to yn, is written as the following. So this is written as Wronskian of sometimes WR is written. A lot of times I'll just write W. So this is Wronskian of y1 to yn of t. This is defined to be, so that's what the colon here means, the determinant of the matrix that is made up of, so the columns of the matrix, this is the easiest way to remember it. Columns of the matrix are y1 of t, y1 prime of t, y1 double prime of t, all the way down to the n minus first derivative of y1. I do that in the next column. So this is the n minus first derivative of y sub 2. I keep doing that all the way to y sub n. So the first row here of this matrix is y1, y2, all the way out to yn. The second row is the row of first derivatives of those things. The third row is the row of second derivatives of those things, and so on. So this is y sub n prime of t, and all the way down to y sub n, or the n minus first derivative of y sub n of t. So I take the determinant of that thing. Okay. All right. So if you don't quite remember how to take determinants, don't worry too much right now, because this is an n by n matrix. You can check. This is an n by n matrix. To talk about determinant, you got to have a square matrix anyway. But this is an n by n matrix. If you know how to compute the determinant of n by n matrix, great. If you don't worry about it, because for the most part, we're going to be doing this for a 2 by 2. And for a 2 by 2, you don't even have to think about it as a determinant if you don't want to. You can just remember what this thing is. But also, the determinant of a 2 by 2 is easy. So then, the big fact, is that y1, the set y1 to yn, is linearly independent if and only if the Wronskian of y1 to yn is non-zero for all t in the interval in question. Now it turns out that if it's non-zero anywhere in the interval in question, then that's enough. But this is non-zero for all t in the interval of definition for the equation in question. Okay. Now, like I said, there's some facts here where for us, for the most part, this is never going to be, we're never going to come across something that's going to trick us here where, oh, we think it might be zero somewhere, but it's not. Usually you can read off immediately that it's not zero everywhere. It turns out that from properties of the Wronskian and various regularity properties of everything involved, that sort of thing can't happen. So it will be everywhere non-zero. When you compute this thing, if it's non-zero even at a single point, it'll be everywhere non-zero, everywhere that's relevant. Okay, and so this Wronskian is a determinant. Okay, and so it might make sense to you, again, as I previously mentioned when talking about linear independence, the determinant was a very important quantity in linear algebra that allows you to take in set of vectors and spit out whether or not they're linearly independent by computing determinant made up of a matrix of those vectors if they're of the proper size. Okay, so that's one way of answering this question. And so that a determinant is related to answering a question of a thing we've called linear independence is not surprising. Let's see how this works in the case n equals 2. So in the case n equals 2, the Wronskian of y1, y2 of t, what is this? This is the determinant of the matrix y1, y1 prime, y2, y2 prime. Sorry, why did I write a prime here? This is just y2. So y1, y2, y1 prime, y2 prime. So this determinant is, remember, the determinant of a 2 by 2 matrix. All right, so determinant of a matrix A, B, C, D right, is AD minus BC. AD minus BC. So this is y1, y2 prime minus y2, y1 prime. So for a 2 by 2, or for the case of a second order equation, the Wronskian takes on this form, which is maybe easier to remember than it coming from this determinant. For me, remembering the determinant helps me to remember what order this goes in. You know, of course, it doesn't matter. Like, you assign what is y1 and what's y2 typically, so this doesn't matter that much. But still, this is just kind of a nice way of remembering what how this thing goes. Okay. So here's the Wronskian. So let's apply this to that example that we did. So I'm going to rewrite all this so that I have room here. So this is the thing that I'm rewriting here. This is the page I'm copying. So we had an example where the differential equation in question was y double prime plus 2y prime plus y is equal to 0. So we had solutions y1. So y1 of t we saw is e to the minus t. That was a solution. y2 of t is the solution 3e to the minus t. And y sub 3 of t is t e to the minus t. So let's show that the set y1, y2 is linearly dependent, and show that the set y1, y3 is linearly independent, and thus forms a fundamental solution set. Okay. All right, so we already saw that all three of these are solutions, so we don't have to worry about that. So then let's compute the Wronskian of these two. So what's the Wronskian of y1, y2 of t? Well, this is y1, y2 prime minus y2, y1 prime. So this is equal to y1 is just e to the minus t. y2 prime is minus 3e to the minus t. Right. Minus y2, which is 3e to the minus t, times y1 prime, which is minus e to the minus t. So this is minus 3e to the minus 2t plus 3e to the minus 2t. But that's 0. Okay. Okay. So this is actually 0. And notice this is 0 for any t. So it's not like it's just 0 somewhere. This is actually 0 everywhere. So that means the set y1, y2 is linearly dependent. As I hinted, you know, geometrically, right? This corresponds to like what happens with vectors when you have two vectors that are scalar multiples of each other, or so that's the case of two vectors. Or for a case of three vectors, right? So if you think about three vectors in space, and I ask you what's the set of all possible linear combinations of three vectors in space, you might say, oh, it's like a, you know, it's like all of space, right? But not necessarily, right? Those three vectors could be kind of generically arranged. Let me write on a different sheet of paper real quick. So those three vectors could be differently arranged like this. All right, maybe something like that. And in that case, the span of these three would be like all of space. But what if two of the vectors, right, or what if all three of the vectors lie in the same plane? So take this piece of paper, right, and I give you three vectors on this sheet of paper. There they are. Right? Well, all three of them lie in this plane, this sheet of paper. So even though this is three distinct vectors, the span of all of them, or the set of linear combinations of all of them, is just this sheet of paper. It's not all of space. Even so, what if these three vectors all lined up like this? What's the set of all linear combinations of those vectors? It's just this whole line, right? So somehow, geometrically, you're not getting enough info for how much you're putting in, right? So what's coming out is not as much as you're putting in. You're putting in two distinct solutions, but then out of it, what you're getting is like one line worth of solutions. Okay, so that's the issue. All right, so these are linearly dependent, so this is not going to form a fundamental solution set. Okay, but let's check the Wronskian of y1 and y3. Okay, so this would be y1 times y3 prime minus y3 times y1 prime. So remember, you can't just do this for any functions. You can only do this for solutions to the differential equation in question. Okay, so these all need to be solutions, but we've already checked. All of these are solutions to that differential equation. So y1 and y3 are solutions already. Y1 is e to the minus t. Y3 prime is e to the minus t e to the minus t, right? All right, and then I'm subtracting from that y sub 3, which is t e to the minus t, times y1 prime, which is minus e to the minus t. So let's see what we get here. I get e to the minus t times e to the minus t, so that's e to the minus 2t, right, minus t e to the minus 2t, plus t e to the minus 2t. These cancel, and I'm left with e to the minus 2t. But guess what? That's non-zero for all t, right? E to the minus 2t is never 0, regardless of what t is. Okay, so y1, y3 is linearly independent. Thus, is a fundamental solution set for the equation. What does this tell me? This tells me that y1, y3 form a fundamental solution set, which means that I can write out the general solution. So then the general solution to this is y of t, which is c1 y1 of t, plus c2 y3 of t, if you like. Okay, because I've labeled them like this. So this is c1 e to the minus t, plus c2 t e to the minus t. Okay. So once you have a fundamental solution set, then the general solution is just the linear combination of that fundamental solution set, the generic linear combination of that fundamental solution set. Okay. But this raises a big question. So computing a Wronskian to tell when two things are linearly dependent or linearly independent, that's one thing. Okay. But how do you actually find these in the first place? How do I find these solutions? Because say that I'd guess this one, right? Well, then maybe the next one I guess is this one, but that we saw doesn't form a fundamental solution set. So I need to find not just any solution to this. I need to find another solution such that the resulting solution set that I get is linearly independent, so I can write out my general solution, right? So how do I do that? So that is going to be a little more complicated, but that's going to be exactly the thing that we focus on going forward. So let's say thus now all that is left to solve these, that is, find general solutions, is to come up with n linearly independent solutions to my DE. Now, I can check the linear independence, so linearly independent, INDEP, there we go. So in linearly independent solutions, I can check linear independence with the Wronskian, but I actually need to be able to cook up these solutions anyway. Right, so how do I do that? So for now, we specialize to the case of n is equal to 2. We will be moving back and forward between this and the generic higher order case. So it turns out that we can see a great deal about how, really when I say a great deal, pretty much everything, we can see a great deal about how the higher order case, the generic higher order case, goes from the simpler case of n is equal to 2. So when I say n is equal to 2, what do I mean? I mean constant coefficient, homogeneous, like this. So y double prime plus a, so y double prime plus, we'll say a1, y prime plus a naught, y is equal to 0. All right, where a1 and a naught are real numbers. Okay, so here's what I'm looking at. Okay, so a big question to answer. How do I construct linearly independent solutions to this? So the answer comes through something called the characteristic polynomial. So I need to look at its characteristic polynomial. Now, even though I said we're specializing to the case n equals 2, I'm actually going to define the characteristic polynomial for any n. Okay. So, but then we're going to immediately specialize to the n equals 2 case, because, I mean, you'll see immediately why this is, the n equals 2 case is big, because it turns out that the resulting equations are the only ones that you've been shown how to solve. For n equals 3 or higher, you don't know off the top of your head how to solve those things. But for n equals 2, you do. In fact, even the Babylonians knew how to solve those. Maybe not your average Babylonian, but at least there was a portion of the scribe class that knew how to do this. So, what is the characteristic polynomial? Let's write out generic nth order equation. So nth order constant coefficient, linear, homogeneous, differential equation. So this again looks like the usual. A2y double prime plus A1y prime plus A naught y is equal to 0. The characteristic polynomial P of z is equal to z to the n plus a sub n minus 1 z to the n minus 1 plus a sub n minus 2 z to the n minus 2, and so on, all the way down to a sub 2 z squared plus a1z plus a naught as the constant term. Okay. So there's the characteristic polynomial. I write out a generic polynomial in z. Okay, and the powers of z are the orders of each of the corresponding terms, and the coefficients are these real coefficients, right? These constant coefficients that I have in my differential equation. Okay. So let's do a quick example. In that previous second order equation, I had, it was y double prime plus 2y prime plus y is equal to 0. The characteristic polynomial, P of z, is z squared plus 2z plus 1. Okay. Now, what is the purpose? Question. Why? The answer, which is going to be my stopping point for today, because I don't think it does a whole lot of good to get into the breakdown of how this works. This will be exactly where I start tomorrow. So the question here, like I said, is why? Like, why am I writing out this characteristic polynomial? And the answer is constructing a fundamental solution set is going to be equivalent to finding roots of the characteristic polynomial. So to give you a preview here, this polynomial factors as z plus 1 squared. So what are the roots? The roots are z is equal to minus 1 and minus 1 to indicate this is a double root, right? And I claim that this has something to do with me being able to say y sub 1 is e to the minus 1 times t. And y sub 2 is, it's a little bit trickier to see why I get this when I have a double root, but we'll go through this later. But I claim that this minus t here is coming from the fact that this is minus 1. And if this were minus 2, right, so if this was z plus 2 squared instead, and both these double roots were minus 2, this would be e to the minus 2t, t e to the minus 2t, for instance. Okay, so this fact that constructing a fundamental solution set to, this sort of equation is going to be equivalent to finding the roots of the characteristic polynomial. So now, if you believe that, you'll see how that works starting next lecture. Right? But if you believe that, you now see why it's important that we restrict to the n equals 2 case, because you might immediately notice, what about the characteristic polynomial? So if n is the order of the equation, Note that the degree of the characteristic polynomial, right, as a polynomial, right, its degree is n, which is the same as the order of the differential equation, right? And so if you have a second order differential equation, the characteristic polynomial is a quadratic. It's a degree 2 polynomial. If you had an order 5 differential equation, then the characteristic polynomial would be a quintic polynomial. It would be a degree 5 polynomial, right? Its highest order term would be a z to the 5th. What's the problem with higher order than 2, right? So for n equals 2, regardless of what polynomial I write out here, I could always use the quadratic formula to solve it, to find the roots, right? But if I talk about cubics and quartics and quintics and higher, you don't really have any general process, right? Any nice thing to apply. Now, if you did, I claim and I will show you how if you did have a way to find all these roots, actually it's no harder than the n equals 2 case. It's the same process. It's literally the exact same process once you are able to find the roots. So finding the roots of the characteristic polynomial tells you everything about how to construct these solutions. So that's what we'll see next time. So I'm going to stop for today and call it. Tomorrow we will start right here with doing a bunch of examples of this stuff. So anyway, so that's the deal. So I'll see you soon. I'm going to hold a little office hour session here right after this ends. So I will see you soon.